Hi, welcome back. Now, what I want to do is have a look at the process of developing software for a board. So let's just have a look at a board. I've got one sitting here in front of me. I'm just going to tilt the camera down now to have a look at this board. There we go. So this board has got a little development board on it. Let's turn on this light, let's get a bit of light on this. So we've got this development board, and in the diagram you've got this here. It's shown as the ES, or Embedded System Development Board here. And what happens is, while you're writing code, you'll have a program such as Atmel Studio open. So I've got Atmel Studio open over here, and I'm going to bring that over and have a look at it. And what you've got here in Atmel Studio is you've got an editor window, and you've got some sort of output window here. Of course, you've got this Solution Explorer, which allows us to see which files we're creating and all that sort of thing. But these are the main parts of our IDE, the editor and the output window. Of course, our IDE is an integrated development environment. It's got lots of different parts to it, one of which is the compiler. Now, the compiler is hidden here. You can look at some of the aspects of the compiler and see what's going on, the tool chain. Here it is. You can look at the C compiler, and it's got all these different features you can have a play with, and that's called GCC. That's the compiler that's built into Atmel Studio. And also there's some programming hardware, programming software built in. Well, in this case there is some programming software built in, but we're actually using another piece of programming software called AVR Dude. So AVR Dude is another piece of programming software, sort of adjoined to our IDE. Our IDE also has a simulator and a debugger built into it. So what happens is, when you write code, it'll go into the code editor, and when you look at the code editor, if you make a mistake in your code, and say for instance you spell while wrong, you'll see that what will happen is it'll give you a little error, and you'll be able to hover over that and see that, well, actually Alt G to jump to a guess, see a list of several, or let IntelliSense try. Okay, well, I know what the issue is there, is I spelt it wrong. Okay, so that's called a syntax error, and so the syntax error is flagged to me in the editor by the little squiggly line underlining the word which is spelt wrong. Now, of course, if we try and compile it and there's an error, then we get a compilation error. So I'm going to compile this. I better introduce a little error in here. So I'm going to comment out this line, which is my header file for where all the definitions are for words like port B and things like that. So when I try and compile this, I go to F7 to compile, it says port B undeclared first use in this function. Well, that's because it doesn't know what it is. So this is a compilation error. Okay, so what I need to do is put this back into the code, and then whoops, leave that in, and we'll just compile it again. You can see, hey, it succeeded in compiling. So there we go. So we've seen a syntax error from the editor, and we've seen a compilation error which has come from the compiler via the output window. Now, if everything's okay, then we can upload it into the programming interface. Now, the programming interface on our board is this little 6-pin header here, and then that will go inside into the flash of the programming memory of the microcontroller. Now, that's all good, but what if we've made some mistakes in our program and it doesn't quite work right? Well, that's a different type of error. That's called a semantic or a logic error, okay? And we need to check that our system works satisfactorily. It has no bugs in terms of its operation, not its syntax, and therefore it's what's happening back here in the IDE, but what's actually happening here in the board. So for instance, on my little board, what I've got is I've got a thermistor which converts thermal energy into some resistance value, which is transferred by a voltage divider into an I/O hardware, and it's read by an analog. So we've got this, basically thermal energy is converted to a number, which is processed by commands which the CPU drags from the flash, and of course these numbers representing temperature can be stored in the static RAM and manipulated, and then we might do something like control some hardware based upon what the level of thermal energy is. And of course it doesn't have to be thermal energy from the LDR, it could be lux or light level from the thermistor, or it could be some other sort of potential mechanical energy that we have converted via some input device into a number. Everything gets converted into a number and is processed, and then what happens is we use that connected via some hardware to an output device. And if you look at my board, I've got output devices, I've got some LEDs, I've also got this little piezo sounder here so I can make some noise, and this is part of my UI or my user interface. And then also my outputs can be connected to something else, and at this stage I've got a little FET on the end of my board for driving other devices like solenoids or motors or something like that. So we might produce some mechanical energy, or I might connect it to a heater and create thermal energy, or I might connect it to my mains power and turn lights on and off, or something like that. Now, if something goes wrong semantically here, it's really hard to see what is going on and where it has gone wrong in the process, because everything in here is hidden from sight. We can't get in here and well, actually we can. There are some ways we can get into this that you need to start to think about. So we can actually connect via a serial communication interface on this. We can connect to a computer via its USB port and run a little program called a terminal program, which allows us to receive and send data to and from the microcontroller. That's one way we could get data out of our program to see what's going on inside it. Another way is that we could put it into a specific test mode, and I'm sure that you have found this before with your phone. If you've ever had to reset it or something, you can go into it and select some particular setup options, or when it's turned off you can hold specific buttons and it will go into a specific mode. So this is sort of like a test mode. You can add LED indicators like a display, or you could send specific messages to the LEDs to say that something is wrong, like it flashes at a fast rate instead of a slow rate, or you could put a 7-segment display on there and it displays codes of things that are not working correctly. An alternative is a debugger, and actually that's a connection back to our IDE, because Atmel Studio version 7 has an integrated simulator and debugger. So if you bought a development board such as the Explained Mini, it has another microcontroller on it, which is a debugging chip. And in the simulator and the editor, you can actually single step the code inside your microcontroller line by line and interpret the values of the registers and see what's going on. So that's another way we can use our embedded system for debugging purposes. Let's go on. Of course, debugging is only important if there's errors, and the best thing to do is actually to spend a little bit of time on prevention rather than a lot of time on trying to cure something. It's much more powerful. And that requires you writing bug-free code. I want you to write transparent code. I want you to be a disciplined and defensive programmer. And that means documenting your code. What it means is making your code so it's reliable and portable, reusable. And when you write code, it's not about code for your convenience, or worse still, writing esoteric code. That is code which is obtuse. Really what that means is it's jolly difficult to interpret what's going on. Don't write that sort of code. In fact, you'll be your own worst enemy, because in 6 months' time you'll want to change the code and you can't even figure out what it is that you wrote yourself. Okay. Naming conventions are incredibly important. Typically, I use lowercase and I use an underscore to separate words. I use full words. I make these things long enough so that they carry the meaning with them, okay? So that they are descriptive names, not temp, for instance, which means temporary or temperature. You're not sure which. When you're doing defines, macros at the top of your code, make sure that these are capitalized, okay? Variable types are really important. Getting those correct requires a bit of thought. Now, if you're going to measure the temperature outside, well, occasionally the temperature outside goes below 0. So an unsigned 8-bit type is not good enough. It needs to be a signed type. It needs to be an int. Now we're going to measure temperature from, if we use an int, then it's going to go from minus 128 to 127. Is that satisfactory? Well, it's certainly satisfactory for a normal sort of thermometer, but if you were trying to measure the temperature of an oven which heated to 350 degrees, then it wouldn't be. And of course, temp is an awful name to choose for something because that really means temporary, and you want to make sure people interpret this as reading temperature. Put one task into a function. I've often made this mistake myself where I'll write a piece of code and I'll put a function together which is doing 3 different things, and then what will happen is I'll come back to it and I'll think, oh, I need to use part of this function for someone else to do something, and then I have to rewrite the function, and it would have just been easier in the first place to make 3 small functions rather than one big one. Okay, so that's really a good thing to do. And when you're writing a function, keep it to one viewable page of code. Don't put too much into it. Okay. Now sometimes you can get away without using braces with an if statement or a for loop or a while loop, and that's where you only have one operation within it. Don't do that. Always use the braces. Don't write code that doesn't have braces in it, okay, to enclose the loop. Now indent your code. Okay, it makes absolutely no sense if your code is not indented. So if I select all of this and I shift, try that all again, control all, and I tab it all back over to the left hand side, it's really hard to see what this means. Okay, tabbing and using indentation, it makes your code so much easier to understand. Okay, whoops. So you know exactly what it's all about, and typically this is handled automatically by your editor. Let's go down, use local variables. Try to avoid the use of global variables. And I've added another one at the end here. When you write a function, functions should not rely on variables outside themselves. You need to pass all the variables you're using into the code as parameters to the function, and not rely on variables which you haven't passed in. Not a good, safe programming practice. You want to learn more about some of these things, and really obvious things actually. Have a look at that book on bargroup.com, their C-style. Now I want to talk about something really important, and that is this concept of state. In an embedded system, what you've got is a system which operates sequentially, and so that means that something that is happening now has an influence upon what is going to happen in the future. So I've got a little board I've made up here using an old board from when I used to teach this stuff to high school students as well, and this is making a little flashing light pattern. Okay, so I've got 15 LEDs on this, and it's just doing this running pattern, and this of course is replicated in the assignment question. So I'll just flick up the assignment question. Here's the assignment question, and what I want to do is I want to step through this and just try and help you understand the concept of state. So I'm not talking about this contextualized understanding of driving LEDs. I'm talking about the whole fact that your microcontroller is in one state, and when you want to move to a new state, that new state has some dependence upon what happened beforehand. So let's have a look at this first. Our first line of code is turning on one LED, and we'll just ignore the delay loops and go to the next line of code, which is turning on 2 LEDs and then 3 LEDs. And what happens in the next line of code is that we want to turn on this LED, and very commonly students will write code that turns on this LED but forgets to turn off this one, and so you'll have 4 LEDs on instead of 3, and that's because there's a sort of subtle assumption that the microcontroller will read your mind. Okay, and we're all inclined to do this a little bit, so we need to be really explicit. Computers are incredibly stupid. They will do only what they are told to do. So if I don't turn off the previous LED, what I'll end up getting is all of the LEDs turning on together, just in a sequence. And I want to avoid that. So what I need to do is, as I keep stepping down here, you'll see that this becomes exceedingly clear when we get to the next line of code after this. Now at the moment I've got this line of code on line 67 in the simulator. I've got that commented out. And so what I want to do is I want to show you what happens if you forget about it. What happens next is you turn on the next LED and you've got 4 LEDs on. You don't want 4 LEDs. So the state of the system at this stage is dependent upon the fact that this LED was turned on and you forgot to turn it off. So let's stop our code and we'll just uncomment those lines. And I'm going to step through this code. And I'm going to step through. And I've got my 3 LEDs on. So the next step is actually to turn off this LED and turn on this LED, which of course, because they're on different ports, one's on port D and one's on port B, these are on need to be on separate lines of code. So it's very easy to forget to do one. And as you go through this code, you will see that we get to the end, 3 LEDs, 2 LEDs, 1 LED, all LEDs off. Then we start to come back down the other way. And we've got our 3 LEDs cycling through this pattern. And then we get to this point in the program where we keep stepping and you can see, oops, there's some code missing in our program and you have to put the code in. And this is where it becomes quite tricky. You have to remember to turn off this LED and this LED on to get this to step to the next point, which of course, because there's a boundary here between these two, if you don't understand implicitly this concept of state, you'll turn on this LED but forget to turn this one off. And so this is how state is sort of exhibited in our program. So state isn't about LEDs going on and off. This is an example of it. State is all about the fact that the system is entirely dependent upon the current state and what has happened previously. Okay? This is the whole idea of state, so that the future of the system is dependent upon what is happening now and what has happened previously. So that's something you're going to have to sort of figure out and work on. Now I'm going to pause this here and we'll split the lecture up into 2 parts before we go on. Cheers.